Hey friends, welcome back to the channel. This video is the second video on rows and mean value theorem from the Calculus Hours video series. In this video, we're going to focus on the proofs of certain equations or inequalities using the mean value theorem. So let's go on with the questions. The first question is going to be, you have to prove that sine of x minus sine of y in a modulo is less than the difference between the x and y. So how are you going to do that? Well, we need to use our knowledge of the mean value theorem. So let's just consider a function of t such that f of t is sine t, because the first thing that you're going to notice in this inequality is that it's something of the sort f of a minus f of b is less than or equal to a minus b. So this is only possible when our function that is of the form sine t, and when we have the domain as x and y. So now we're going to consider that the mean value theorem is valid on this function, because it is indeed valid since sine t is continuous between the x and y, and it is differentiable as well between the domain x and y. So let's move on to what the mean value theorem used to say. Mean value theorem used to say that we have a point C such that its derivative at that point is equal to the secant line between the maximum minimum point of the domain. This is going to be f of y minus f of x over y minus x. So f bar of C, which means, okay, so what's going to be f bar of t? It's gonna be the derivative of sine t, which is with respect to t, which is cos t. So what's gonna be derivative of the function f of t at point C? It's gonna be f bar c, which is cos c. Now what we have is f of y. F of y is gonna be sine y. F of x is gonna be sine x over y minus x. Now what we have is, okay, so we need to prove, sorry for this, we need to prove an inequality that has modulo signs. So let's just insert the modulo signs over there. So we have cos c modulo equals modulo sine y minus sine x over modulo y minus x. Now we know that cos c lies between 1 and -1. However, when we take the modulo of this, everything that's gonna be less than 0 is gonna convert to a number that is greater than 0. However, the magnitude of the number is gonna remain the same. So now what we're gonna have is the domain of cos c, the range of cos c is gonna lie between, is gonna be less than 1 and greater than 0. So it's gonna lie between 0 and 1. Now when this whole thing is equal to cos c, we're gonna say that sine y minus sine x over y minus x, which is equal to cos c, is always less than or equal to 1. So now what we have is sine y minus sine x is less than or equal to y minus x. Now, well, what we needed was sine x minus sine y. So we're gonna take the negative sign as common, and it's gonna turn into positive because we have a modulo sign. So we can just write it down this way. And ta-da! We've proven our problem. Now let's move on to the second problem. The second thing that you have to prove that cos of ax minus cos of bx over x is less than b minus a. So what we have is, okay, now again we have something of the form that is f of x minus f of y. Well, if we multiply this x over there, we're gonna get the angle. So what we're gonna say is, this is something of the form f of x minus f of y is less than x minus y. Sorry, y minus x, or it's the same thing because we have the modulo. So the next thing that we have here is, we're gonna suppose a function t such that f of t is cos t. And we're gonna say that this function lies between a certain domain, that is from ax to bx. Now what we're gonna say is we're gonna assume that the means value theorem is valid on it, considering the fact that the cos t function is continuous between ax and bx because it's continuous on every x, and this function is differentiable between ax and bx because it's differentiable on every x. So now what we're gonna do is we're gonna use the mean value theorem. It says that there exists a point c such that the derivative of the function at that point is equal to the gradient of the secant line. So what we have is f of bx minus f of ax over bx minus ax. So let's substitute the f bar of c. So we have f of t as cos t, so we know that f bar of t will be equal to negative sine t, because the derivative of cos x is equal to negative sine x. Now we're going to substitute c in place of t, and we're going to say this is equal to negative sine c. Now what happens is negative sine c equals f of bx, that is cos of bx minus cos of ax, divided by x times b minus a. Now let's go on to what we want to prove. What we want to prove has the modulo signs. We're going to take the modulo now. The modulo of negative sine c is going to be sine c. It's going to be equal to cos of bx minus cos of ax modulo over modulo of x times modulo b minus a. Now we know that sine c lies between 1 and negative 1. However, the modulo of sine c lies between 1 and 0. So what we have here is this particular function is less than 1 over modulo of x times b minus a. This is less than 1. So what we're going to do is we're going to write it as cos of... Okay, so now I think we're done, because now the only thing that we want to do is rewrite things. So we're going to say this is less than or equal to b minus a modulo. Now since cos bx minus cos ax is inside the modulo, so if you take a negative sign as common, it's not going to result in anything different. So we can just rewrite it in the form cos ax minus cos bx. And since there's a modulo on x as well, we can take it inside this and make it a fraction inside a modulo, which is what our question requires. Let's start with the next question on the topic mean value and Rolle's theorem. The question is, you have to prove that tangent of x plus tangent of y modulo is greater than or equal to x plus y. So what we're gonna say is basically that let's consider a function t such that f of t is tan t. Take its derivative just in case. This makes it sec square t. Now let's first look at what this question looks like. So basically what this question looks like is something of the form f of x minus f of minus y, x of minus minus y. So it's basically something that lies inside the domain x comma negative x comma y. Basically what the mean value theorem says is that you have a point c between negative x and y such that f bar of c equals f of y minus f of minus x over y minus minus x, and substitute the function in place of f bar of c, which is gonna be sec square c, and it's gonna be equal to f of y, which is tan y, minus f of minus x, which is minus tan x. So minus minus makes it a positive number. And then the denominator is going to result in y plus x. So now you have the exact function, but you want the modulo in that. So you're going to say sec square c modulo is equal to tan y plus tan x modulo over modulo y plus x. Now what we're going to have is, we know that sec square c is equal to 1 over cos square c. And we know that cos square c lies between 1 and 0, because cos c lies between negative 1 and 1, and when you square a negative number it turns into a positive number. So it's gonna lie between 0 and 1. And if you divide 1 by a number that is between 0 and 1, so you're gonna get a number that is greater than 1. So sec square c is gonna be greater than or equal to 1. Now when we've got a limiting factor for sec square c, we're going to substitute it in here. We're going to say that sec square c is equal to 10y plus 10x modulo over y plus x modulo. And since sec square c is always greater than 1, we have modulo 10y plus 10x greater than or equal to modulo x plus y or y plus x, and that's what you wanted to prove. Now let's move on to our next question. The question says that you have the inequality 1 plus x to the power alpha greater than 1 plus alpha x, and the question says that alpha is always greater than 0. Alpha is always greater than 1 and x is always greater than 0. Prove that this inequality is true. You have to prove that this inequality is true. So how are we going to approach this problem? Well, it's nothing of the form f of x minus f of y, y minus x or something like that. So we don't know what to assume the function to be. So we're going to just write function of t to be as 1 plus x alpha minus 1 plus alpha x in the brackets, right? So when we can't can determine the function, we just write it in this form, that is generally. So what we want to do now is find its derivative. Its derivative is gonna be the following. So what we want to do is, we want its domain to be between 0 and x. This is what we're supposing right now. So now let's just apply the mean value theorem on it. We're considering the lowest limit as 0 because it's gonna make our things easier for us. Because since the difference is gonna be x. So what the means value theorem says is that there exists a point C such that the derivative at that particular point is equal to the secant is equal to the gradient of the secant line. Right? So it's gonna be this. Now let's substitute in the values. What we get here is alpha 1 plus c alpha minus 1 minus alpha, which is equal to 1 plus x alpha minus 1 plus alpha x, and f of 0 is gonna be, well, it's gonna be 0. You can calculate it later on. So this is why we took 0 as the lowest limit, because it's gonna make things easier for us, and we always try out stuff that can make things easier for us. So what's gonna be b minus a is gonna be x. So now we have alpha x 1 plus c alpha minus 1 minus alpha x equal to 1 plus x alpha minus 1 minus alpha x. This and this cancels out. Now what you have is, okay, let's move it up there, and now what you have is, you have alpha x 1 plus c alpha minus 1 plus 1 is equal to 1 plus x power alpha. Okay, so now you can see that this is forming much more like this. except for the fact that the right thing has 1 plus c to the power alpha minus 1. Now we know what we want to replace in this equation to make it an inequality. So it's going to be this term, right? Because it does not exist in the original function that we want to prove, in the original inequality that we want to prove. So now what we have is, we have 1 plus c to the power alpha minus 1, and we know that alpha is always greater than 1 because it's given in the question. So we know that c lies between 0 and x, c is always positive. So when c is always positive, 1 plus c is always greater than 1. And when a certain thing is greater than 1, when 1 plus c is greater than 1 and it's raised to the power that is greater than 0, so it's always going to result in a thing that is greater than 1. So what we have here is, you have 1 plus c to the power alpha minus 1 greater than 1. So let's just make this the subject in this equation, and we're gonna substitute the greater than 1 over here, and that's gonna end up giving our results, hopefully. So what we have here is, okay, let's just do it some other way. We know the substitution way. What's the other way that we can do it? Okay, well, so basically, consider you have alpha x and you have alpha x times 1 plus c alpha minus 1. You know that 1 plus c alpha minus 1 is greater than 1. So of course, alpha x is going to be less than a alpha x 1 plus c power alpha minus 1, because this alpha x is being multiplied over here to a number that is greater than 1, so it's always going to result in a value that is greater than alpha x. We also know that alpha x plus 1 is less than then by alpha x 1 plus c to the power alpha minus 1 plus 1, because it's just the one that you're adding on the both sides, so it doesn't make any difference. This value is greater than this, and we know that this particular value equals 1 plus x to the power alpha. So 1 plus x to the power alpha equals alpha x times 1 plus c to the power alpha minus 1 plus 1. So, and this particular value is greater than this. So this particular value is again greater than alpha x plus 1. To write it simply, we say consider this function as f of x, this as g of x, and this as h of x. We know that f of x equals g of x. We also know that, well, we know that h of x is less than f of x. So, and f of x equals g of x. So, if you substitute this, if f of x is greater than h of x, then g of x must also be greater than h of x, right? So this is what we've done. If f of x equals g of x, f of x is greater than h of x, then g of x is also greater than h of x because it's equal to f of x. That's what we've done, and that's it for today's video. Bye.